9. In this lecture, we will introduce a new technique for problem solving called dynamic programming. So this technique is basically using tables to store some intermediate results of the previous computation so that we can speed up the future computation. We will talk about 3 different problems. The first one is how to find the nth Fibonacci number. And then we will talk about a problem called assembly line scheduling. And finally, we will give an example of an interesting puzzle about dividing gold coins among 5 pirates. So let's start. Now here we define the Fibonacci number Fn as follows. Okay, so F1, the first Fibonacci number, is set as 1. F2, the second Fibonacci number, is also set as 1. And for all other n greater than or equal to 2, the value of Fn is simply the summation of the previous 2 terms, Fn-1 and Fn-2. So based on this definition, the first few Fibonacci numbers are, so this is 1, 1. If we have these 2 ones, then we will get the sum which is equal to 2. Then we get a 2 here. 1 plus 2 will get a 3. 2 plus 3 will get a 5. And then we get an 8, 13, 21, 34, 55, 89, and then 144. Now, because Fibonacci number is defined by a recurrence relation, so it is very natural that we can solve it by using a recursive algorithm. So this is a C or C++-like code. So we want to find out what is the Fibonacci number f of n. So in case n is equal to 1 or n is equal to 2, then we will simply return 1 immediately. This is the basis of the Fibonacci number. Otherwise, which is not these 2 cases, we assume that n is always a positive integer. So otherwise, if it is not these 2 cases, then we will just find out what is the value of f of n-1 and what is the value of f of n-2, and then we sum them up. Now we can easily show that the previous method is correct by using mathematical induction. It is because this program or this algorithm is correct for computing f of 1 and f of 2, because both of them have value equal to 1. And then assuming that this program correctly computes all the values from n is equal to 1, 2, 3 up to a certain value of k, then in that case, when we want to compute the Fibonacci number of f of k plus 1, then we can use this formula, which is a correct formula based on the correctly computed value of Fibonacci of k and the Fibonacci of k minus 1. So these are the previous values which are assumed to be correct by the induction hypothesis. So we know that the f of k plus 1, the new value, can be computed correctly. So the correctness is easily shown by using mathematical induction. And then how fast does this program run? So if we use t of n to denote the running time to compute f of n, then we will see that t of n is equal to the time to compute f of n-1, so it's t of n-1, plus the time to compute f of n-2, which is t of n-2. And after computing these 2 results, we add them, so there is a plus 1 for the time. Now notice that this is actually the same form as we define the Fibonacci number. So we actually can solve this exactly and find that t of n is of theta of f of n. But then f of n is a function actually that grows exponentially with the base of the golden ratio 1.618. So f of n is roughly of the order of 1.618 to the power n. So that means that if we use this recursive algorithm to compute f of n, then the running time is exponential. However, we can find that there is a better way to compute fn. We can actually compute f of n in linear time. The idea is just compute f of 1 as 1 and compute f of 2 as 1. And then, based on the computed values of f1 and f2, we can add them and then get f3. And now we have f3. We have f2 already. So by adding f2 and f3, we get f4. And so on and so forth. So in the end, when we have already computed the values of fn minus 2 and fn minus 1, we simply add them and then we get f of n. Now we will see that this latter method is much faster. Yeah, the earlier method runs in exponential time, but the latter method runs in linear time only. Now the major reason that it is faster, it is because we have stored the previously computed values. So by the time we need, so for instance, by the time we want to compute f3, we assume that f1 and f2 are already there, and we have already stored them. So immediately we can add them and get f3. Once we have this f3, we will store it. So later, when we compute f2 plus f3 to get f4, the values of f3 is already there. So in that case, when we have already stored all the previously computed values, then it will speed up the later computation. So by the time that we need that, all the previously stored value can be retrieved in constant time. On the other hand, if we look at the first method, the former method, so in this former method, this is the computation of f of n minus 1. But then we have never stored all the results that we have obtained in the intermediate computation. So by the time when we compute f of n minus 2, so nothing was left. So we have to restart the computation again. So in such a case, we have wasted a lot of time to recompute the same value of f again and again. Okay, so this is the idea of dynamic programming. So usually we use DP as a short form for dynamic programming. So it is not really related to programming. So don't worry, we are not talking about programming in this class. But then dynamic programming is just a technique that we use extra space, and usually in the form of a table, an array or a 2D table or whatever table, so that we can store the intermediate results, and then these results can be retrieved later so that for future computation. Now, for a problem that dynamic programming can help, it usually will have two properties. The first one is it would have something that we call optimal substructure. So the best solution for a larger problem depends on the best solution of the smaller subproblems. So this is called optimal substructure. Now, if there is optimal substructure, usually our problem can be solved by using the recursion idea. And also, we will have overlapping subproblems. So usually, the same subproblem will be seen again and again, so that by storing the intermediate results, then we will be able to speed up the later computation of the same subproblem. So when we have overlapping subproblems, it will be good if we use table to store the intermediate results, so that later we can get speed up. But here, I want to make a comment. Okay, so usually the most difficult part to solve a problem using DP is to think of what kind of intermediate results to store, so that we can solve the original problem based on the stored values. And usually this is the most difficult part. It is because this needs creativity. Nobody tells us what kind of results should be stored. And by studying the problem long time enough, we will be able to somehow get some idea, some insight of what are the relevant results that we need. So in that case, then we will be able to obtain speed up. So there is no quick route to get a success for applying dynamic programming, and we have to make a lot of practice so that we will now be familiar with this technique. Once we know what kind of values that we should store, and usually the dynamic programming problem can be solved very easily. The other part will be very easy. So we will have some practice in this lecture, and also we will have some other practices in the coming few lectures.